Yeah. Thank you all for coming to attend my talk. As I said, my name is Mark Hammons. Quick bit about me. I was born and raised in the American South and lived in Oklahoma and Texas. I moved to France when I was about 27, finished my master's degree. I'm currently working for Ingenico Terminals as a tech lead, and I have a beautiful wife and a 1-year-old daughter. And I'd like to thank both Ingenico and my wife and daughter for supporting me today. I want to talk about the problem space that Slinc is trying to deal with. I'm sure you're all familiar with the many platforms that Scala is running on. You have the default platform for Scala, which is the JVM, but you also have the ability to target JavaScript with Scala.js and native with Scala Native. And using each of these platforms has strengths and weaknesses. If you're running on Scala.js, you can use Scala or JavaScript libraries. You can write code that runs in the web browser. If you're writing in Scala Native, you can use C libraries, and you have very quick startup times and stuff like that. However, if you want to use Java libraries and you want to have multi-threading and stuff like that, typically you need to be using Scala on the JVM. So the problem is that maybe we don't want to just use Java libraries or Scala libraries on the JVM, but we want to be able to use C and other native libraries. And accessing these kinds of libraries on the JVM is historically very difficult. And maybe also you would like to access native memory easily. There's been ways in the past to do this using technologies such as JNI, JNR, JNA, Java CPP, Bridge, and Foreign nowadays. But the problem with these is that they're all heavily Java focused. They're not particularly easy to use from Scala, and some of them require additional C++ compilation phases or another language compilation. For example, JNI, Java CPP, and Bridge. So the niche for Slinc is that it's Scala-oriented, focuses on ease of use. There's no additional C++ compilation required to actually call into C code, and it focuses on type safety that is absent in the other libraries I mentioned. So, Slinc has a number of goals, and those goals are as follows. It aims to be ergonomic, attempts to use Scala concepts wherever possible to bind to C. It's deeply multi-platform. It attempts to adopt them and maintain the Java mantra of write once, run anywhere. It has support for multiple JVMs, and it is attempting to be performant. And I would like to point out that Slinc is Scala 3 exclusive because without Scala 3, Slinc would not be able to achieve its ergonomic goals, it would not be able to achieve its performance goals, and I don't think it would be able to achieve its multi-platform goals. Though Scala 3 still has some shortcomings and pain points that I've had to work around. So, let's go ahead and look at the ergonomics of Slinc. Here we have the definition of rand in C, and it's just a function that returns an int. If you wanted to bind to the standard library and call rand from Scala with Slinc, you would define a trait to house the method, derive this fset type, and then you can summon and you would define a method that mirrors the shape of the C. You use the same name, rand, and a similar return type, int. And then you can summon an instance of something that looks like test that has a rand function, and you can return a random int that was generated by C. And that is a very simple hello world C binding in Slinc. If you wanted to create an analog of a struct in Slinc, it's fairly simple as well. You have here a struct named myStruct. It has a first field named A, that's an int, and a second field named B, that's a float. And the equivalent in I lost my code there for that. Okay, well, we'll go ahead and look at a different example then. So here in C, we have the definition of div. which is a function that takes a numerator and denominator and returns div t, which has the quotient and the remainder inside of it. And binding to that in Slinc looks like this. So you define a case class. The name is not important. All that matters is the shape, which is specifically it has two integer fields, and that it derives the struct type class. That marks it as a struct and usable with C bindings. Then we define a trait. The name of the trait doesn't matter, just that it derives fset, and that has a method div that takes two ints and returns the div t type. Then we can instance that trait and call the .div function, and we get back from C our case class filled out with the result, which is div t 2 and 1. The quotient is 2 and the remainder is 1. I think this is a good time to start talking about the two types of memory that you have to deal with when you're programming in Slinc. You have the JVM heap and the native heap. JVM heap is where all the Scala objects and references are stored by default, and we're all very familiar with using the JVM heap. However, when you're using Slinc, you also have to deal with the native heap. That is data allocated outside of the JVM heap, where C can access it. And Slinc typically, when you're dealing with Slinc, you're copying data out of the JVM heap into the native heap, or out of the native heap into the JVM heap. So we can look at how we can do that specifically. Here in Scala with Slinc, we are allocating a pointer, and we do that by using something called a scope. This is the confined scope, which allocates memory that is confined to a specific thread. And we can copy data, specifically the value 5, into the native heap using this pointer.copy functionality, which produces a pointer of int. And then we can copy the data back out of the native heap back into the Java heap using the unary exclamation mark to dereference the pointer that pulls the data back out of the native heap. And now the result of that is assigned to I, making I equal to 5. When you're dealing with pointers, it's important to remember that the native heap and the JVM heap are separate. So in this example, we're going to mutate some data on the native heap, and we will see that it doesn't affect anything that's on the JVM heap. Here we have an array. It's an array of 5, 6, and 7, and we create a scope as before. We copy the array into the native heap using pointer.copy, and for that we get a pointer of int back, because in C typically an array is viewable as a pointer to some type, not as an array type specifically. So the equivalent in C is a pointer. And here we offset to the second element of the array and assign that value 8. So now in native memory it's an array of 5, 8, 7, and then we pull it back out of native memory with p.asArray and the size of the array, which is 3. So then the result of the scope is that we get an array 5, 8, 7 and assign that to array 2. And if you look at the bottom of the code example, you see that the second element of array is not equal to 8, but the second element of array 2 is equal to 8. So the mutation of the data on the native heap did not affect the JVM whatsoever. We can see here how in Slinc you can copy strings into C and back out. You use the pointer.copy method as before. This returns a pointer of byte. The reason for that is because in C, typically a string is a pointer to a character, but in Java, a character is 16 bits long as opposed to in C, where it's typically 8 bits long. So if we used a pointer to char, this would not be an appropriate mapping because those are 16-bit values in Java as opposed to 8-bit values in C. So the appropriate mapping is pointer to byte. When you have a pointer to byte, you have a special method on that pointer called copy into string. You provide the maximum value or the maximum length you want to try to copy. If you try to copy from native memory and you don't reach the terminating byte, which is 0 in C, it'll stop trying to copy after 256 elements. But when we copied into C, we had the terminating byte put into the native memory. So we copied into C native memory hello world. We copied back out hello world, and that's the value of our string in I. So when it comes to passing arguments to methods in Slinc, generally you have pass by value and pass by reference. Anything that's not wrapped in a pointer type is passed by value, always. So if you have a struct, if you have an integer, float, whatever, and you pass it into a method in Slinc, or a method bound by Slinc, it's going to be copied into native memory and then given to C. But if you pass in the pointer, it'll pass in a reference to the value, and the C function can modify and mutate the data at that pointer, and you can view those changes by dereferencing. So we can look at an example of how that would work by creating a binding to sprintf. This will also provide an example of how variadic parameters work in Slinc. So definition of sprintf in C is that you take or give a character pointer to string, which is a blank array with the maximum size of the string you want. You provide a formatting string, and then you provide data to be formatted and inserted into the original str value. And the return is the length of str. So, in order to bind to this, we would define sprintf with the method name as always. The first element, or the first parameter would be a pointer to byte. Second parameter would be a pointer to byte. And then for the variable args, you would use a sequence of variadic. This is a special type I've created in Slinc that captures information about types passed into the sequence, specifically that they are compatible with C. So stuff like structs, the basic types, stuff like that, and if they're compatible, it copies that information and how to send them to C in this variadic type. Once we've instantiated our test type, we can create a scope, create a blank array of like 256 bytes so that we have a potentially very large string. Create a formatted string where we have as the first element, or the first thing is going to be an integer format, and the second is going to be a float with a precision of 2 decimal points. And then we pass in our data. So we pass in the string pointer, the blank string pointer, the format string, and then our data to be formatted, which is 5 and 2f. And if we use copy into string from string pointer, we get back 5 space 2.00. So I'd like to go over why it's important for Slinc to have multi-JVM support at the moment. So Slinc is powered by the new foreign API in Java 17 and greater. And this API is an incubator API in Java 17 and a preview API in Java 19. And what that means is that it changes all the time between the JVM versions. So here I have a definition of, or I have a binding in Slinc, And I would like to show you how that maps to the foreign API in Java 17 and Java 19. So on Java 17, you have to import jdk.incubator.foreign and java.lang.invoke.methodType. You call system.load with the library name, and then you call clinker.getInstance.downCallHandle. You provide to symbol lookup the name of the method you want to look up, the method type that represents that method. So method type that takes or returns an int and takes an int using these class of ints. And then finally a function descriptor of clinker, cint, clinker.cint. And then you have a method handle that you can use something like invoke exact to get your result back. In Java 19, this changes. So instead of being in jdk.incubator, now it's in java.lang.foreign. And you do system load as before, but now instead of clinker, you have linker. Instead of get instance, you have .native linker. And you don't even pass in a method type anymore. And you also, instead of having cint, you have value layout.javaint. The shape of the code has completely changed. Where the pieces you need are located has completely changed. And so generally, for each of these, you have to write a specific instance of how to call into them. And Slinc specifically takes great pain to actually abstract that from the user. So at runtime, it will detect, okay, you're running on Java 19, and it'll load the appropriate code generation that uses Java 19 as opposed to the Java 17 versions. I also mentioned multi-platform support for Slinc, and what I mean by that is in Java, generally, we can write our code once, and in theory, it will run on pretty much every platform. The same doesn't work so well for C. So, for example, we have this very simple function definition in C. You pass in a long, you get a long as a return. So the question is, how should this be bound in Slinc? You could bind it like this in Slinc. However, if you do that, now you have binding that is platform dependent. This code would work on Linux and Mac x86, but it would crash on Windows x86 because the long type in C is only guaranteed to be 32 bits long, and on Windows 64-bit, long is 32 bits. It's about equivalent to an int. So the problem here is that the long type in Java is always 64 bits, and there's a mismatch of the widths expected. So here, you're trying to pass in a 64-bit value to something that's expecting a 32-bit value, and that causes the crash. So how would we resolve this in Slinc? Well, Slinc has path-dependent types, or I'm calling them platform-dependent types, such as C-long. Their value, or their definition changes based on the platform you're currently running on. So on Windows, this C-long is equivalent to an integer, but on Linux and Mac, this C-long is equivalent to a long. And with this type, Slinc is able to generate the appropriate bindings and send only a 32-bit value, and you'll have type-safe code, and your code will not be platform dependent anymore. So the final thing I'd like to talk about is the performance of Slinc. With the JVM multi-platform support and the multi-JVM support, all of this requires a lot of abstraction. And as I'm sure you're aware, abstraction is kind of the enemy of optimization and performance. So as an example, if I wanted to, I have a struct here, I want to be able to copy it into native memory, and I would like to do it as performant, as quickly as possible. Well, the code that you would write by hand with the foreign API would look something like this. And this code is about as close to the best code you could write for something that would write data into this A value into native memory. However, it's got a problem. It's platform specific to begin with, and you're making assumptions about the platform you're running on. Slinc takes a lot of pain to not make those assumptions, and the problem in that ends up causing the code that's generated at compile time to look like this. And this is like page 1 of 5 pages of code that does the same thing as the tiny little snippet I just showed you for the handwritten code. So how is it possible that it's getting meeting the performance goals? Well, it's not if you're just using the compile time generated code, which is why I stopped trying to do that. Instead, I use something in Scala 3 called runtime multistage programming to do Jit compilation. At first, Slinc uses the compile time generated code and it instruments it. If that code is called, let's say 10,000 times, then it sends to a embedded Scala compiler in Slinc a request to generate optimized code for your platform. The compiler runs on a dedicated thread. It does the optimization and the compilation in the background, and once that's finished, it swaps out the compile time generated function with a runtime generated properly optimized function. And that function ends up looking like that. So this is code that's actually generated by Slinc, by Slinc's Jit compiler. It has constant folding. It is able to generate code that is pretty much exactly equivalent to the handwritten code, except even though this is making assumptions that, for example, C long is equivalent to long, this is safe because at runtime it knows that C long is equivalent to long because it's running on this. At this point it was running on Linux. If I ran this same code on, or this same compilation on Windows, it would know that C long is equivalent to int and cast it to int and make the appropriate conversion completely safely. So how does the performance weigh, or how does it do compared to the compile time? Well, it's about 20-30 times faster than the compile time code. It's not quite at the level of the manually written code, but that's because there's harnesses I've put in place that have to be optimized, and I'm sure that I can optimize them further to get them closer, but there's always going to be a little bit of overhead because it's doing swapping out and stuff like that, while the manually written code, you just have it in place and known from compilation time. But in any case, with this Jit compilation, I'm able to reclaim a lot of the performance that you would get with the manually written code without having to manually write it. And it ends up without the harnesses, I've found that it's about 80% the speed of the manually written code. Now, the reason why I do the Jit compilation instead of just doing all the compilation at startup is because I have the Singleshot comparison here of the various approaches, and you can see the compile time, write manual, and Jit compiled all have very low Singleshot time of like, let's say 10,000 microseconds per operation on a cold JVM. While if I'm using just I immediately compile everything for one invocation, this ends up being like 70,000 microseconds. It's much slower because the Scala compiler itself is fairly slow. So the reason why I took the Jit compilation approach is because we want to not have a startup overhead when you're running. We want to only compile the things that you're actually using super frequently. Otherwise, the compile time version should probably meet your needs if you're just calling it one single time. it still runs in on the order of microseconds. So it shouldn't be a big problem if it's only one call. And that's my talk.